I'll go ahead and start early to answer your question. So is from where? 5-1? No. 5-1? No. 4.7. And number one? Which one?
4.
Oh, okay. Yeah. I see what you're saying. Yes. Okay. Yep, that's it. So you've got cube root of x squared and then plus x times root x.
That's what I did.
Yeah. That's right. So you have to get these to look like powers of x. So this one is x to the 2/3. Plus x times x to the 1/2. And then when you put these two together, since that's a power of 1, you're going to add the exponents. So you get x to the 2/3 plus x to the 3/2. And then you can use your power rule.
So because they're multiplying, you can add the...
That's right.
Nice.
Yep. Yeah, because otherwise it would be hard to undo that, like to try and do the antiderivative.
Yeah.
We don't have a technique for that yet. So, and then from there, you're okay?
Yeah, because I read the chapter, I was like, there's nothing that
Yeah.
I was doing the product.
Yeah, any problems in this section are going to require that you rewrite them as powers of x. I mean, there's no other thing that we have yet.
Okay.
But today I will introduce you to a new technique.
Cool.
So. Was there any other questions? You just stop somewhere.
Okay.
C6, 4, 15. Okay. What's that?
Are we doing that one question?
Are we going to do that one question?
Yeah, the 1 plus 2 plus 3,
Uh-huh.
the -12.
I'm going to start with that. Yeah.
Oh.
Yeah. Oh, no, not that one.
Yeah, I was like...
That's forever. That's summing forever. The one that's negative 1/12, that one that I showed you, that's if you never stop the sum. Here we're going to stop the sum at n. See? Yeah, I'm not going to get into that. I'm not going to get into that today. No. Okay, let's get started. Well, you know what? Let me see if this is locked. Okay, so we have our final next week, right? So we only have 2 more class periods. And today I'm going to cover some stuff. I mean, this is still tied into last class. I want to do a little bit more with the Riemann sums. And then we're going to, I showed at the very end of class last time how the antiderivative allows us to basically do everything the Riemann sum does. But I want to show you at least one problem using a Riemann sum. I want you to see how bad it is, and then it will make us really appreciate the fundamental theorem of calculus. All right? But to do the Riemann sum, I need to first establish something, a couple of things first. And this is actually the first thing I want to establish, and that is, well, how should I say this? This doesn't seem like it's related to what we're trying to do. Okay, this should seem like, what? This is a totally different problem. But we're going to need this to do the Riemann sum, all right? So there's a story that goes with this. I always tell my students about this. I don't know if it's a myth. People argue that it is a myth. That there was a first grader back in the late 1800s. I might have that wrong too. But anyway, his last name was Gauss. And there's a story about him that when he was in first grade, the teacher came into the class and asked the students to find this sum. Okay? So basically told the little first graders, hey, you know, what's 1 plus 2? And they said, 3. And he said, what's 1 plus 2 plus 3? And they all sat there and said 6. And then the teacher said, all right, I want you to add up the first, well, actually, the teacher wanted them to go out to 100. That's what it was. So the teacher said, go out and add up the first 100 digits, right? And the idea was that he was trying to give the students some busy work, all right, to keep them busy. Maybe he had a bad weekend. He wanted to just give them something to do, right? So the story goes that within a few minutes, one of the students, Gauss, finished up, and they used to write on little chalkboards? Little, yeah, it's like a whiteboard nowadays, but they were called little slates. They had a little slate, and they would write with chalk, and then when they were done, they would turn them over, and they'd just sit there. And so the story goes that within a few minutes, Gauss turned over his little slate and sat there, and the teacher went over to Gauss's slate and turned it back over, and this is what Gauss had written on the slate. N times n plus 1 divided by 2. That's what Gauss had written down. And so the teacher got all upset because this formula is actually the formula that you need to add up the first n numbers. So if you wanted to add up the first 100 numbers, like the assignment that the teacher gave them, all you'd have to do is replace this n with 100 and calculate it, and that's the sum. And we can check it. Let's check it for this one right here. Here n would be 4, right? Let's see if this formula works for 4. We plug 4 in here, we get 4 times what? 5 over 2, and that's 20 over 2, it's 10. So it appears to work for that. And we could try it for 5. Let's see, if we put 5 in there, it's going to be 5 times 6 over 2, that's 30 over 2, that's 15, so it matches for that. So it looks good, right? Now, this formula was known, okay, so Gauss was not the first person to ever come up with this. And the teacher was very upset because he's like, who showed you that formula? And Gauss insisted that nobody had shown him the formula and that he had come up with it on his own. And so I'm going to show you how he came up with it and how he explained to his teacher how he came up with it. And let's see if we can follow it, all right? You ready?
Sure.
Okay, so here's what Gauss did. He said, look, I'm trying to find the sum 1 plus 2 plus 3 all the way out to, I'm going to go with 100, okay, because that's what he was asked to do, right? So Gauss said, all right, that's what I'm trying to find, right? Let's call that S. And then Gauss said, well, with addition, it doesn't matter which order you go in, right? You can go the other way. You can add it the opposite way. And let me come down here. The last one would be 1, wouldn't it? The one in front of that would be 2. The one in front of that would be 3. Yes? And then up here, let me give myself a little more room. This would have been 100, right? The one in front of it would have been 99. The one in front of that would have been 98. And so Gauss said, all right, I can add it either way, right? Count up or count down. And then Gauss did this very brilliant thing. He said, all right, what I'm going to do is I'm going to add these two together. So I'm going to add s plus s. That should give me two s's, right? And then he said, I'm going to add these just straight down. So what's 100 plus 1? 101 plus, what's 99 plus 2? 101 again. This is the key. 98 plus 3, 101 again. And then keep going. And then all of these are 101s, aren't they? Aren't they all 101s? And now the next big key point of this is how many 101s does he have there? How many are there? Well, there's one of them, there's two of them, there's three of them, and there's 100 of them, right? There are 101s. So if you were asked to add 101 100 times, that's the same as multiplication, right? If I say add 5 4 times, that's 4 times 5, yes? So this is really 2 times s equals 100 101s, yes? And then we want to know what s is, so just divide by 2. So 100 times 101 over 2, right? That makes sense? Okay, so I lied to you though, all right? That's not what Gauss showed the teacher. I always have to show that first to make sure everyone can follow it, right? This is what Gauss did. Because Gauss had a formula, right? N times n plus 1 over 2. So what Gauss actually did was he did this. He said, I'm going to add the first n numbers, okay? Let's start over. And so I want to stop at n, right? What would be the number right before n? N minus 1, 1 less than n, right? N minus 1. What would be the number right in front of that one? N minus 2, yes? And then he said, all right, I'm going to write that sum down again, but I'm going to write it backwards. So the last one should be n, and the one right in front of that, or after that, would be n minus 1, and the next one would be n minus 2. And then you get all the way down here, what would be the last number here? 1, and then the one in front of that would be 2, and the one in front of that would be 3. And then he goes and says, I'm going to add straight down again. So when he adds down, n plus 1 is n plus 1. Plus n minus 1 plus 2. n minus 1 plus 2 is still n plus 1. Next one, n minus 2 plus 3 is still n minus 1. Or sorry, n plus 1. And then all the way down to the very last one, which is n plus 1. Right? How many of them does he have? 1, 2, 3, 4, 5. N of them, right? He has n of them. So s is equal to n times n plus 1. Sorry, 2s. Forgot to add this side, sorry, 2s. And that's twice what he wants, so he divides by 2. And s is n times n plus 1 over 2, which is the formula. Y'all follow that?
Yeah.
So that's what geniuses do in first grade. Okay, that's brilliant, isn't it? Because you can follow it. I mean, I can tell by that you look on your face, most of you follow that. And the fact that that's what makes geniuses geniuses, is that they can make something that appears very complicated, they can find a solution that's relatively easy to follow. It's that actual connection, doing it, right?
Didn't Zach tell us he did this in kindergarten?
Who's that?
Didn't Zach tell us he did this in kindergarten
Who?
last semester?
Who told you that?
Zach.
Zach, oh, God.
Did he try to tell you? He was like, yeah, I did something like this. And he was like, no, you didn't.
Was he still there when I was talking about this? I thought he had his headphones on. I'm not sure he was paying attention. Okay, so this is pretty cool, right?
Awesome.
There's another way to do it if you ever, if you're wanting to show your friends. There's another way to do it visually, which I think is a little easier for some people to follow. People who are not necessarily math people. And you can do it with like little boxes. Like here's a box, right? 1, and then there's another box. There's 2, and there's 3, and there's 4, right? Let's do one more. 5. So we're trying to add up how many boxes is this, right? This is basically 1 plus 2 plus 3 plus 4 plus 5. Yes? Okay, so what you could do is you could make a carbon copy of this picture, all right? So just right-click, copy, right-click, paste, yes? And then flip it over. So here's 1, here's 2, here's 3, here's 4, and then here's your 5, right? Yes? So how many are in each column here? 1, 2, 3, 4, 5, 6. So start out, this was 1, right? Yes? And then you're adding the 5, so that gives you 6. Here we have 6, 6, 6, 6. How many of them do we have? We have 1, 2, 3, 4, 5 6s, don't we? So imagine that this, I'm kind of pushing here, but let's see. I'm saying imagine that this went to n, that I had this stacked n high, right? Then wouldn't this be n plus 1? It'd be n of them in the red and then plus 1. Then this would be n plus 1 again. N plus 1 again. Then how many would you have? You'd have n of them? That make sense or no? If it doesn't, don't worry about it. So this is n. This is n plus 1. But I duplicated it, right? I doubled it. So I have to half that. So if you do this times this and half it, you get back the black part. Anyway, okay, you can mess with that yourself. All right, cool? Good? The sum of the first n integers is n times n plus 1 over 2. Got it? All right, now, next question. What's 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, all the way out until you get to n squared? So this is not the sum of the first n integers. This is the sum of the squares of the first n integers. Right? Understand? Sure? So this one is harder to show, all right? I can show it visually, but it takes me drawing like a three-dimensional pyramid. So it's a little harder for me to show. So I'm just going to have you take the formula on faith. Okay? Can you take it on faith? Believe that it can be shown. It's n, Hold on. Hold on. 2n plus 1. Hold on. I just got to double check it. I don't want to put the wrong information out here. These are very well-known formulas. Yeah, okay. That's what I thought. N times n plus 1 times 2n plus 1. So that's the sum of the first. The sum of the squares of the first n integers is going to be that formula. So let's just check it. What would 1 squared plus 2 squared plus 3 squared be? Well, that's 1 plus 4 plus 9. That's 14. Okay? What was n for us here? 3. Okay, so if I plug 3 in here, I get 3 times 3 plus 1 is 4. And then 2 times 3 is 6 plus 1 is 7. And then all that divided by 6. And I believe that's 12 over 6, 2 times 7, 14. Yeah, it works. Okay, so it worked, right? Okay. You just have to trust that it works for every single n out there. All right? All right, so I've given you 2 formulas so far. Yes? We're going to do one more formula. The sum of the cubes. 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed plus dot, 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 all the way to n cubed. This formula is a lot easier to remember. It's n times n plus 1 over 2, which is that formula, right? Squared. It's kind of weird, but the sum of the first n integers is this, and the sum of the cubes of the first n integers is this, which is just that one squared. Just turns out that's what it is, okay? So I've given you now 3 formulas. Yes? Okay. All right. So I needed that. Now we move on. We're going to do Riemann sums.
So where did he actually find the formula? Did he really just make it up?
Yeah, and that's the story. Yeah. Now, if you remember in college algebra, when you were learning how to solve systems of equations, you learned this method called elimination. It's actually named after the real technical name for it is Gaussian elimination, and we're talking about the same guy. So he went on to do very, very brilliant things in mathematics. He's one of like when you look at all the big mathematicians, like in his century, he was in the top 2.
Oh, wow.
Yeah. So he's well known, very well known. Yeah. Yeah. Okay, so yeah, if he's doing that in first grade, you can imagine what he's doing when he's in his 20s. All right, so I'm going to get back to Riemann sums. And I'm going to try and see if we can't come up with a general formula for finding the area underneath the curve for any curve. All right? And then I'm going to give you an example, and give you a specific function, and we're going to try and calculate the area under it. All right? That's what we're going to do. And then once we're done, we're going to use the antiderivative to verify our answer. And we're going to say, yes, the antiderivative was much more efficient. All right? So let's see if we can do this. We'll start out with a picture. And this is going to be a pretty detailed picture. All right? I have a function. I'm going to start it at a. Notice I'm not starting at 0. I'm just going to start at some arbitrary value a. I'm going to end at some arbitrary value b. And I'm going to throw some function up here that goes from a to b. And we're trying to find the area underneath that curve. All right? That's the goal. So we already talked last class that what I want to do is cut it up into rectangles, right? Cut it up into rectangles. If I do one rectangle, it'll be pretty bad. 2 will be better, 3 will be better. The more, the better I'm going to get, right? And the idea is that could we let the number of rectangles go to infinity? Yes? Okay, so let's start by cutting up this line segment into n pieces. So I'm going to cut that up into n equal pieces. And I'm not telling you what n is, all right? So imagine I'm going to make equal cuts in here. And let's just act like we don't know what they are. We just know that this creates n segments. Got it? What is the width of each segment? So if I asked you, take this little segment right here and tell me how wide it is, what would it be? Well, how long is the interval? How long is this interval? Okay, it's always better if we do an example next to it. Let's see. If we had 2 here, let's say we had 7 here. How long is that interval? 5, right? All you do is take that, subtract that, right? So I'm going to take that 5 and cut it into n equal pieces. So it wouldn't be 5 over n? Yes? So this right here is going to be the length of the interval, which is b minus a over n. Each one of these is that wide. Agreed? Okay, I'm gonna call that something. I'm going to call that delta x. Delta standing for change. Right, so my change in x, every time I jump from one to the next, the change that I'm having in the x is by this amount, b minus a over n. Yes? All right, so now I'm going to try and draw my first rectangle. And what I'm going to do is I'm going to start at the right endpoint of this interval. I'm going to go straight up to the function, and then that's going to create my rectangle, right? Let's talk about this. We'll call it R1, R subscript 1 for rectangle 1. Tell me about the area of rectangle 1. So I need to do this on the side here. What is the area of rectangle 1 equal to? Area of rectangle 1.
A minus b over 1.
Well, how wide is it?
1n.
How wide is it?
Triangle x.
It's b minus a over x, b minus a over n, right? Or delta x, right? That's delta x. So I'm going to say delta x is how wide it is, right? That's my width. But how tall is it? How tall is this? It's the actual, this is the function f, right? So it's the function's value. Where though? Okay, good. It's not happening, we're not picking this point, right? So it's not happening at a, it's actually happening at a plus delta x. Do you agree? It's a, but then I added one jump to it. Yes? Sure? Okay. So this is f of a plus delta x. That's how tall that rectangle is. With me? Sure? Okay, so I'm going to put that here. F of a plus delta x. Darn it, got to squeeze that in there. All right. Now what we would do is we would go to the next rectangle, right? The next rectangle, I'm going to start at this point, go up and over, right and down. Before I do that, can you tell me what that point is? I know how wide that is already. That's delta x, right? It's not what I'm curious to know. I want to know the actual point because that has to get plugged into the function. So where am I now? I'm a plus 2 of those delta x's, right? So I start out at a and then I move over 2 jumps. So this is the point a plus 2 delta x. You with me? What would the next one be while we're doing this? What would the next one be? This would be a plus 3 delta x, right? And just out of curiosity, what would this last one be? Well, we know it's b, right? I mean, it's b, but it should be a plus n delta x's, right? Now check this out. This is really cool. What was delta x? It was b minus a over n, right? Wouldn't these n's cancel? And then wouldn't you get a plus b minus a? And the a's would cancel and you just get b. So it actually works. Like the very last endpoint should be b, and if I plug everything in, I do get b. What I need you to see here, though, the pattern is that your first rectangle, this is going to be one of those delta x's. The second rectangle, you're going to be at 2 of those delta x's. Third rectangle, you're going to be at 3 of those delta x's. Make sense? Sure? No questions? Okay, so I think maybe you can give me the formula for the area of rectangle 2 now. It should be f of a plus what? 2 delta x, and then times the width, but the width is still delta x, right? And then the area of the third rectangle should be f of a plus 3 delta x, and then times delta x. Now remember, this right here, a plus 3 delta x, a plus 2 delta x, a plus delta x, those are numbers, right? And they're being plugged into a function. We don't know what the function is, but this is what we're doing. We're evaluating the function at this point. That gives us the height of the rectangle, and then the width is the same for all the rectangles, okay? All right, just out of curiosity, what would the area of the kth rectangle be? Kth rectangle. So it's f of a plus k delta x times delta x, all right? Make sense? All right, so let's now try and add these up. So if I did this, right, if I did this for n rectangles, so there's n rectangles in here, n rectangles in here, n rectangles, then the area, right, the true area, okay, the true area underneath this curve. I already know I'm going to have mistakes because all of this little error that I have in there, right? The true area would be approximately, that's my approximate symbol, the sum. Now, have y'all seen the sigma notation? Do y'all know how that works? I'm going to try, if you have never seen it, then I'm going to try and show you how it works right now. So what it's going to be, it's the sum of all of these, right? I've got to add up all these. So there's something common in all these formulas. They all look like this, don't they? All that's changing is the k. It's the only thing that changes. So what I'm going to do here is I'm going to say it's the sum of all of these things that look like this. And I'm going to start k where? Where do I want to start k? What's the number that would go into the first formula? 1, and then it'll become a 2, and then a 3, and then a 4, and it's going to stop where? At n. So what I do is on this sigma notation, I say k equals 1, and then the top I put n. So this tells me where I'm going to start k. I'm going to start k at 1. So what I do is I write this down. Let me erase. Now I'll come up here. So this is basically saying what I'll do is I will start with k being 1. That's f of a plus 1 times delta x times delta x. And then I say plus, because this sigma notation means addition. All right, there is one for if you wanted to do like something times something times something instead of add. There's a different notation you'd use. It's capital pi. That's our product. So if you did k equals 1 to n, this would be multiply times, this times this times this. And you won't mess with that, so don't worry about it. But so I'm going to say plus, and now I let k become 2. And then I say plus, and now I let k be 3, and then 4, and then 5, and then 6, and I go all the way to what? I stop at n. Okay? So do y'all see how this is a very condensed way of writing out a big string of things? Okay. So that's it, right? My area is approximately this. Agreed?
Yeah.
Okay. This is the formula I want you to box for right now. And now we're going to do a specific example. You ready? Remember what delta x is. You know what? I'll put it over here so we don't forget. Remember that delta x is b minus a over n. Okay, here's an example. Approximate area under f of x equals x squared minus 1 on the interval 1, 3. We'll give ourselves some easier numbers to work with here. Hold on, let me look at something real quick. Yeah, okay, that'll work. This is kind of interesting. A real quick sketch. This function goes like this, doesn't it? Whoa. Yes? And what's its value at 1? See, we're going to start at 1, right? So at 1, we're at 0, right? And then we go out to 3, and we're trying to find this area right here, aren't we? Okay, so that's what we're trying to do. Okay, according to our formula, the area should be approximately equal to the sum k equals 1 to n of f of, okay, a plus, well, we know what a is, right? What's a? A is 1, and what's b? 3. Hey, if we have a and b, don't we have delta x, kind of? What's delta x? So that's 3 minus 1 over n, right? Which is just 2 over n. Okay, so what I'm going to do is, in this formula, I'm going to replace a with 1. I'm going to replace all my delta x's with 2 over n. Make sense? So this will be f of, where am I? A, which is 1, plus k times 2 over n. Right, like that, then times 2 over n. Y'all okay with that? Okay, now what we're going to do is we're actually, because we know what the function is, right? We are going to plug this into the function. Because we have a specific function we're looking at now, right? So watch how this changes. This is equal to sum k equals 1 to n. And if I asked you to plug this into the function, you would square it and subtract 1, wouldn't you? So let's go ahead and square that. It's 1 plus k times 2 over n squared minus 1, but then all of that still times what? 2 over n. Okay, so the 2 over n's here. Does everyone understand the f is gone now, right? F is gone because I've evaluated the function at this. Now, I don't know what it is because I don't know what k is, I don't know what n is, but that's what would happen to it. I square it and then send it through, right? All right, let's actually square this. Let's square this. We'll do it over here. What is what is 1 plus k times 2 over n times itself. 1 plus k times 2 over n. So 1 plus k times 2 over n plus another k times 2 over n, and then this last one plus what? K squared times 4 over n squared. That okay with you if I do it that way? I just squared each one of them. What happens when you add these two together? Because they're exactly the same, right? I get 2. Well, this is 2 of these, right? And this is another 2. So I put them together, I should have 4. Yeah. So how about I write it this way? How about, I guess, I'll do it this way. K times 4 over n. And then plus k squared times 4 over n squared. Is that still all right? Sure? All right, that goes here, right? That goes right here? Oh, sorry, that goes right here. I still have minus 1 here. So this is going to be sum k equals 1 to n of 1 plus k times 4 over n plus k squared times 4 over n squared. All right, that's this piece, right? Then what? Minus 1. But then all of that times 2 over n. And the 1's cancel, don't they? Does anyone have any questions?
Tons.
I remember when I first saw this, I was just like, whoa, just all these symbols and everything. It's a little overwhelming. Are you all following it, though? You're okay? Just want to make sure you're following the algebra, because really that's all I'm doing at this point. I'm evaluating a function at some expression. There it is. I expanded it. There it was. Putting things together, right? This is where I am, right? Okay, let me try and clean that up a little bit. I'm going to squeeze that in right here. All right, so I have the sum k equals 1 to n, and I've got, can I take this and now distribute this through like this in here, because those ones were gone, right? I should be able to do that, right? So if I multiply 2 on top here, won't that become an 8? And that n on the bottom will become an n squared. Yeah. So how about I write it this way? K times 8 over n squared. And then here, when I multiply from here to here, that'll become an 8, and that'll become n cubed, won't it? And I'll still have the k squared out front. So plus k squared times 8 over n cubed. All right, so that's what I'm trying to do, right? If I could compute that, if I could, then I would have an approximation, wouldn't I? When you look at this sum, k is the thing, k is what we call the index. K is only affecting that piece and that piece, right? The 8 over n squared has nothing to do with k. Do you agree with that? Like as I change k, 8 over n squared doesn't change. 8 over n cubed doesn't change. So watch what I do next. This is kind of the cool part. So this is equal to 8 over n squared times sum k equals 1 to n of k, and then plus 8 over n cubed times sum k equals 1 to n, not to 1 to infinity, 1 to n of k squared. So it's kind of like when we were differentiating or integrating. We haven't done a lot of integration, but I've told you like constants come along for the ride. N, right, wherever I'm going to stop, the number of rectangles has been determined. It's going to be 100 rectangles or 1,000 rectangles, 1,000,000 rectangles, whatever, right? But that 8 over n squared is a number. It's a constant. And I will basically multiply my k by that constant every single time. This has the same effect. If I let k be 1, then I'm going to hit it with this, right? And then I'll let k be 2, and then I'll hit it with this. then k be 3, and then I'll hit it with this. So it has the same effect. Does that make sense?
So just keep doing it until you get to n.
Until I get to n, right? Now, this is we're at the big point now. Do you know what this is? And do you know what this is? So just tell me, if I asked you to take the sum from 1 equals to n of k, I would start out by doing what? 1, right? So this right here, forget this for now. If I said do this, it would be 1 plus what would be the next one? 2 plus what would be the next one? 3 plus, where would you stop? At n, wouldn't you? Isn't that what I started class with?
Yes.
Isn't this the form, like Gauss had a formula for this? It was n times n plus 1 over 2, right? And then what about this one? This is 1 squared plus 2 squared plus 3 squared plus 4 squared all the way to n squared, and I gave you the formula for that one. I told you we needed them. This is where we need them, okay? So now, using those really nice formulas, watch what this becomes. The area is approximately 8 over n squared times this sum, which is n times n plus 1 over 2. Do you notice that the summation, the k is all gone now? Okay, that's what we needed. And then what is this sum? So I have plus 8 over n cubed. That was n times n plus 1 times 2n plus 1 all over 6. And we no longer have k's. So our area is approximately this. You just give me an n now, and I will have my approximation. All right? Is that okay? Yeah, so if somebody said, hey, use 100 rectangles, I would replace all my n's with 100 and I would get an answer, right? Now, the computer, I had the computer kind of do this already for us. Yeah, I should be able to erase a lot of it. Let me erase this so you can kind of see this over here. Now, unfortunately, I think in this example, I'm starting out at 0, not at 1, and I'm ending at 5. So let me see if I can't tweak my code real quick. I don't know. I haven't been into this code in a long time, so let me see if I can figure it out real quick. 0 to 5? Maybe. There's more code to it than this, so let me see here. 1 to 3. Oh, I think that may have done it. Yeah, okay, cool. That did it. Okay, so now, unfortunately, because I didn't have time to manipulate this, this is 1, okay, everyone? This is 1, and this is 3. So in our picture, remember our parabola started here and then went up? That picture you see is only showing from 1 to 3. It's only showing this, okay? It's not showing this over here. With me? Okay, so if I were to replace n with 10 rectangles, then if you plug 10 into all of these, it would spit out 7.48. Okay? Do you believe that it would? Can we just, all right. Now if I let n be, let's say 45, right? Look at now, see the error that I have, E-R-R-O-R. The error I have is getting smaller. All those little gaps there. Okay, now the area is 6.8451. It's better. Well, we don't know what the real area is yet, right? Now if I let n go to, I've only got this to go to 70, because at some point you're not going to be able to see it anymore. Let's see. Shall we go bigger? Let's go to 500. As a maximum. But again, you're going to see that when I do this, at some point it's going to be hard to tell. So here we go, 27. So look at that. Okay, my computer is going to start having trouble here. But do you see how the more rectangles you have, the closer you get to the true area? Yes? And that if you could go to infinity, you would have the area. Now, the problem that we have, the problem with the idea of going to an infinite number of rectangles is that each one of our rectangles had this b minus a over n is how wide it was, right? Delta x. And if I let n go to infinity, this expression goes to 0, doesn't it? Because b minus a is a constant, and you have a constant over infinity that goes to 0. So the width of your rectangles is going to 0, and if my width is 0, then I have no area, right? But that's what calculus allowed us to do, is to get past the idea of when we had things like 0 over 0, right? We could do that. Or if we had infinity over infinity, we could do that, right? It's approaching something. Now, right now you might say, look, well, how could we ever get around the constant over 0? Constant over infinity, that goes to 0. How are we going to get around that? Well, look at our formula. Look at our formula for the approximate area. Look at this thing right here. This is what I'm focusing my attention on, right? Yes? Okay, so that's really, I don't care about the width of the rectangle going to 0. I do care about it, but at the end of the day, this is what I need to do, right? I need to take this and let n go to infinity. So the true area is equal to the limit as n goes to infinity of the sum as k equals 1 to n of f of a plus k times delta x times delta x. So that's the formula I gave you before, right? To the right of my hand, that's the formula that we did, and we said that's the approximate area. All we have to do is add a limit out to the front. If we add the limit, that will give us the true area. So let's go back to this, and let's take the limit as n goes to infinity. Is that fair? Let's take the limit as n goes to infinity of this. So I'm trying now to find the true area, and it should be the limit as n goes to infinity of this expression. Ooh, let me clean this up. Can I, before I do it, can I cancel this 8, make it a 4, and cancel that? Is that okay? Can I reduce this out, make that a 4, and make that a 3? Is that fair? Okay, so I'm trying to take the limit as n goes to infinity of 4 times n plus 1 over n squared plus, let's see what's here, 4 times n plus 1 times 2n plus 1 all over 3n cubed. Okay, so all I've done is just kind of clean that up a little bit. Do you agree that's what I'm trying to figure out? All right, let's take the limit and see what happens. Where does this numerator go as n goes to infinity? What's infinity times 4 times infinity plus 1? That's infinity. On the bottom? Infinity. Infinity over infinity? L'Hopital. L'Hopital, right? This one is infinity over infinity also. L'Hopital. But before I do L'Hopital, let me actually clean it up. I'm not ready to take the derivative of the top there. I'm going to write that as 4n squared plus 4n over n squared. So what did I do here? Just distributed, right? Now on this one will be a little bit harder. I'm going to distribute first 4n squared plus 4n, and then I still have to multiply it by 2n plus 1, don't I? So like I'm distributing this through. That gives me this. And then I'm going to FOIL those. So what should the numerator of this one be? 8n cubed? 4n squared? 8n squared? So 12n squared? And then last one, 4n? And that's all over 3n cubed. Now I'm ready for L'Hopital, because now I don't mind taking derivatives of tops and bottoms anymore. So the next step by L'Hopital's rule is the limit as n goes to infinity. Okay, what's the derivative of the top here? 8n plus 4. And the derivative of the bottom, 2n. Over here, derivative of the top, 24n squared plus 24n plus 4. Derivative of the bottom is 3 times 3, 9, right? Okay. 9n squared. Okay. Next. still infinity over infinity. L'Hopital again. L'Hopital again equals, by L'Hopital's rule, limit as n goes to infinity. Oh, that. So derivative of the top of this one is 8. Derivative bottom of that one is 2. So 8 over 2, which is 4, plus, next one, 48n plus 24 over 18n. Right? Okay, this is 4, right? Yeah. This one is still infinity over infinity. So I got L'Hopital one more time, but don't touch this one. This one's still 4, right? 4 is 4. So when I do L'Hopital again, limit n goes to infinity, I have, let me put those in parentheses. 4 plus 48 over 18. Why didn't it go to 0? Yeah. Okay, because think of these as two separate problems, okay? Just look at these as two separate. I'm trying to take the limit of this and the limit of that. What's the limit of this one going to? 4, right? So we're done with that one. Like n is no longer there, right? That's going to 4. We're happy with that. This one we didn't know. We had to do another application of L'Hopital. But the fact that this is 4, we've already resolved that. Does that make sense? Okay. So this is okay? Does that reduce? I think number goes into that. What, 6 go into that?
Yep. Yeah. Yes.
So it's 3 on the bottom and 6 goes into 48 8 times. So 4 plus 8 thirds. So common denominator, we get 3 on top, 12 thirds plus 8 thirds is 20 thirds. 20 thirds is what I'm getting. Okay? 20 thirds. The true area under that curve is 20 over 3. And as a decimal, what is that? 20 over 3. Like 6.666 again. Okay, so 6.666. All right, so if we go back to our picture, the Riemann sums here. I know it's very hard to read. Okay, I'm sorry I didn't do this before class. We've estimated the area with 300 rectangles. We have estimated it to be 6.6667. I mean, we're already pretty much there. The true area, the actual area is 6.666 forever. It's 20 thirds. That's the true area. See, now if we would have gone with less rectangles, okay, there we go. So with about 19 rectangles, we're at 6.6648. So we're not quite, we need more rectangles. If we let it go to infinity, we get the exact answer. Now, do you see the work that was required for that? Okay. So now, we're going to do it with the antiderivative. And I've got to show you a theorem first. I kind of showed you last class. You can imagine that the Riemann sums could get pretty nasty, right? All right, so some notation. If you are asked to find the antiderivative of a function f, we write this. I did not show that to you last time, right? Or did I? I did not, right? Yeah. Okay, so this is, you know how in the previous class I said, hey, here's little f, right? Find its antiderivative, which turned out to be capital F of x plus c. Okay, so every single time I told you, hey, find the antiderivative, find the antiderivative. Well, instead of saying that every time, if you just write this down, that means find the antiderivative. All right? It means, hey, here's your function f of x. This means find the antiderivative of it, okay? The dx, I'm going to explain where it all comes from, but this is the notation we use to let you know to find the antiderivative. So this sign right here, this symbol, is called the integral sign. Of course, this is the function you're going to find the antiderivative of, right? That's called the integrand. It's kind of like when you did radicals. Whatever's underneath the radical is called the radicand. Well, whatever's inside the integral sign is called the integrand. And then this right here is going to become important later. This is called your differential. But for now, just look at it as, I want you to just think of this as the thing that tells you what your variable is. So x is the variable in the problem, all right? So this just verifies that that's what it is. All right, so there's the notation we use, okay? So let's just practice with this notation. If someone were to say, for example, that would be asking you to find the antiderivative of the function we just did, right, a second ago? But this is just going to give you a capital F of x plus c, isn't it? So the answer to this should be what? 1/3 x cubed minus x plus c. That's from last class. That's your power rule from last class, right? Okay. Everyone good with that? All right. Now, I give you the theorem. It's called the Evaluation Theorem. And the Evaluation Theorem is a version of what's called the Fundamental Theorem of Calculus, which you'll worry about that in Cal 2, all right? But this theorem is used a lot. So here's what it says. To find area under F, and I'm going to be clear on that, between F and the x-axis. We use the following. I forgot to tell you where we are. Oops. Okay, well, it's all right. I'll draw it with the picture. So we have a function between a and b. Here's our function f, and we're trying to find this area in here. Okay, so in my picture, I've put a to b, all right? That area, I'm out of room, so I'm going to put it over here. That area is equal to that's the antiderivative, right? That's the antiderivative of this function. But there's some other elements I need to add to this notation. At the bottom I put a, at the bottom of the integral sign I put a, top of the integral sign I put b. And by putting those two numbers in there, that changes everything. That no longer means you want to find the antiderivative. That means you want to find the area, right? Because didn't I just do this problem a second ago without the a and the b? And you told me the answer was 1/3 x cubed minus x plus c? By adding two numbers, you are no longer looking for the general antiderivative. You're trying to find the exact area underneath this curve. All right? This is known as the upper limit of integration. And this one is the lower limit. Is that all right? Same thing, lower limit of integration? So what is that? I mean, this should give us the area, right? But how do we calculate it? How do we calculate it? So here's how it's done. This